So consider this scenario. We have a relation R from some set to itself, and we've seen some properties that R could have, right? It could be symmetric, it could be reflexive, it could be transitive. But let's suppose that it doesn't have some property that we really want. For example, I really want R to be symmetric, but it's just not. So what can I do? Well, we're going to talk about a general solution of that in this unit. And what we're going to do is we're going to start with R, and then we're going to do something to it. Generally, we call that taking a closure of R. And we're going to take a closure so that we do end up with some property that we want. For example, I want a function, rather a relation that generalizes R in some way, but that it is transitive. Okay. Now, that's actually easier to do. It's really easy to do if you don't play by the rules. So the most trivial thing to do is just to say, oh, well, let the closure of R be all of S cross S, right? The entire cross product. Well, if it's the entire cross product, then guess what? It's symmetric, right? Because if AB belongs to R, that means that AB is a tuple in the cross product. Well, so is BA, because it's just another tuple. And awesome, right? So it's definitely symmetric. How about reflexive? AA. Well, that's one of the tuples in the cross product. So yes, it's in this quote closure. So that wouldn't be fair. Okay. So what we're going to try to do is we're going to restrict ourselves to small extensions of R that will actually give us the property that we want. Okay, that's very important. Okay, so let's start with reflexivity. Okay. What is the reflexive closure? So what we want the answer to be is this. We want it to be the smallest, and that's a keyword there, the smallest and reflexive relation that extends R. Okay. So what do I mean by extend? Remember that R is a set of tuples. So something that extends it is like a superset, right? So the reflexive closure is going to have all the tuples in R and then a few more. So here it is. Right? Notice that it's R union something, so it extends R, right? And then this is what we're adding. We're basically adding just the smallest possible reflexivity, right? This is S comma S such that S belongs to our set, capital S, right? So yeah, let's, if we go with that, right? I think it's easy to see that it's reflexive, but why should it be the smallest reflexive? Well, we could argue that informally, and here's a good argument. Okay, so like I said, it's obvious that it is reflexive, and that's just because this part right here, that is reflexive, right? And so when I add anything else to that, I end up with a reflexive function, with a reflexive relation, I should say, because all of all that reflexive means is that we should have the all the tuples S comma S, right? So we already have them. That's great. Okay. Now, how do I know that it's the smallest one? Here's the approach, right? So I'm going to have this thing, which I'm going to call R, right? And I'm making it bigger, okay? Because I've added all the S comma S tuples, right? So now I have something that's bigger than R, okay? Now, let's suppose that I find something else, like here, okay? And this also extends R, and it's reflexive. Okay. Now, for one thing, let's look at a point right here. That is one of the small reflexive points that should actually be there. And if you believe that, then you see that that this thing actually has to include all of these as well, right? Has to be like that. And once you believe that, then it's clear that this is actually the smallest one, right? Because everything else has to have something bigger, right? So let's make that a little bit more formal. So what we say is, okay, so let's say that T is a reflexive relation extending R. We're calling this T over here, right? So let's first of all look at some point in here, okay? Right? This is a point in our extension, right? Okay? And what we're going to see is that if it's that extension, since it's a union, there's only two cases to consider. E could actually come from the original relation R. And if it does, then of course it's also in T, right? Because T is some extension of R. Okay? Now the other possibility is that E looks like S comma S because it's in this union, right? So that means that E has to be in here, and if it's in there, then it's equal to S comma S for some S belonging to capital S. Okay, well in that case, it also has to belong in T. And why is that? Because we said that T was reflexive. So it contains all of those things. So what we have is that our solution, right, has to be a subset of that one, right? So if we have some other reflexive relation that extends R, our solution has to be inside of that. So that's why it's the smallest one, right? Because it's actually contained in or a subset of any other one that has those properties. Okay, I realize that's a subtle argument, but it's kind of a clever argument, and it's one that I want you to be able to reproduce. Okay, all right. So let's do another example here. Let's take R being just less than, right? So X R Y if and only if X is less than Y. Okay. So what is the reflexive closure? Well, it's gonna have less than, right? And then we're gonna extend it to have all those S comma S tuples. Those are the S equal to S or X equals Y entries. So what we end up with is actually just X is less than or equal to Y, right? So that's nice, right? That's our extension, and it's very natural, right? If essentially if I start with some relation R, when I take its reflexive closure, what I end up with is R or equal, right? Okay. So here's a simple example of that. Same idea. So let's say that R is actually proper subset. Okay. So now I'm talking about sets, right? So for instance, what I might be able to say is that 1, 2 is a proper subset of 1, 2, 3, 4, 5. Okay. So that's my relation. It's a relation between subsets. And what we'll say is, what's the reflexive closure? Well, that's proper subset or equal, right? Which is actually just subset. Okay. So that's two examples of taking the reflexive closure. I want you to have some intuition for what it does. But when it comes to proving that you have the right answer, you have to go back to the previous definition. So you have to show that it's actually, the smallest set that has that property. I've already shown you that that smallest set is always equal to the original relation R union the set of all S comma S. Okay, so let's try symmetry, right? What's the symmetric closure? Again, it should be the smallest symmetric relation that extends R, right? That's you're going to be hearing that a lot. It's the smallest something relation that extends R, right? Where the something is the something closure of. So we claim that it actually looks like this. Is R union the set of all B comma A such that AB belongs to R? Again, here's the real question. Why is that the smallest symmetric relation? Okay. Well, I think you should be able to do this answer by yourself at this point. So I'm going to ask you to, right? Basic hint, do the same thing or try to do the same kind of argument that we had before. So we start with our relation R. Then we're going to add to this, right, all of the B comma A pairs, right? And now what we're going to argue is that if you find something else, right, some other relation that also extends R is going to have to look like this, because it needs to have all of R, right? And it also needs to have all these tuples, right? Because those are the ones that force the symmetry. So this is the smallest, right, relation that has that property. Okay, so I want you to be able to follow that argument, and I don't think you'll have a big problem with that. Okay, so some examples of symmetric closure. Let's take less than. So what we're going to do is we're going to think of less than, A is less than B, and then we're adding to that B is less than A, right? So that's what we have. Well, that's actually all of the elements that are not equal. So when we take the symmetric closure of less than, what we actually get is less than or equal to. Okay. Suppose we do subset, right? So now I have all the sets A, B such that either A is a subset of B or B is a subset of A. That's not the same as saying that A is equal to B. Okay. So what we have is what's known as comparable. And for instance, if I have these two sets here, 1, 2, then 1, 2 is a subset of 1, 2, 3. These two sets are comparable. It is also the case, of course, that 1, 2, 4 is a superset of 2, 4. So again, those two are comparable. But if I look at something like 1, 2, 3, right, then that is not a subset of 2, 4. Okay, and 2, 4 is not a subset, or rather a superset of 1, 2, 3. Okay, I should have just left the direction go identical. Okay, and so those are actually not comparable. You know, I can't compare the two because neither one is, quote, smaller than the other. So yeah, that's those are examples of symmetric closures. Okay, so our last big one is transitive closure, right? So the transitive closure is, this is a definition that you should just spit out by this point. It is the smallest transitive relation that extends R. I don't have a quick way of showing you what that is. So instead what I'll do is I'll kind of show you in pieces, okay? So I'll start by defining what R1 is. And R1 is just R, okay? And once I have R1, then I'll show you what R2 is. So I start with R1 and then I union something. And what I'm unioning is all of the pairs AC that have this property. AB belongs to R1, BC belongs to R, okay? Notice here that that is not R1, okay? It's R, all right? And so so there must be some B that kind of combines the two in that way. From A I get to B using R1, and then from B I get to C using R. That means that AC should be in R2, okay? And then once I have that, then I'll move on to R3, and it's the exact same definition. R3 is equal to R2, okay, what we had before, union, the set of all AC, such that AB belongs to R2, BC belongs to R, okay, again, not R1 or R2, okay. So we're just adding kind of another R at the end, and we just keep expanding that way, okay. So once we have that, then we generalize what we mean by Rn, and Rn is just Rn minus 1 union set of all AC, such that there's some B that from A I'm related to B using Rn minus 1, then from B I'm related to C using just plain R, okay. And so now what exactly is the transitive closure? By the way, this is so common that we actually have a symbol for it is R with a superscript plus, okay. And R plus right here is simply defined as the union of all these, right? So realize that the union of all this is going to be R sub infinity if there were such a thing, but there isn't, okay. So we just add union R1 with R2, with R3, with R4, with R5, with R6, and so on, and that's the answer, okay. Okay. Why is this the smallest transitive relation that extends R? Okay, let's break that into two pieces. Why is it transitive? Shoot, that's actually hard, okay. And smallest, it's even harder. We actually don't have the machinery to be able to prove this. We're going to have to wait for a little while until we learn something magical called induction. At that point, we'll be able to prove this. So I'm going to leave this. Yeah? We'll take care of this later. Okay. Example, let's take less than, okay. The transitive closure of less than is actually also less than, okay? And that shouldn't be a big surprise. Less than is a transitive function. So since this already has the property that I want, I don't need to add anything to it in order to get the property, right? So let's try a different one. Let's try parent. So x is related to y if x is a parent of y. So what is the transitive closure of that? Well, it ends up being ancestor, because it's parent or a parent of that parent or of that parent or of that parent and so on. It's exactly what we mean by ancestor. And let's try prerequisite, right? X is related to y if x is a prerequisite for y. Transitive closure of that, basically that's a course you should take before taking course y, right? So it might be a direct prerequisite, or it might be a prerequisite for one of those, or a prerequisite for one of those, and so on, right? So you can see that these notions actually appear very naturally from applications. All right, I want to finish with reflexive transitive closure. And in here what I'm doing is I'm taking the R, and what I want to find is actually, right, you should have this, is the smallest reflexive transitive relation that extends R. And the way that we're going to find it is it's pretty simple. We're going to start with R, and then we're going to take its transitive closure, R plus, right? So we want reflexive transitive. That kind of gives us the transitive part. And so then we add S comma S such that S belongs to capital S. This takes care of transitive, and this takes care of reflexive. Okay, and you can actually, you could do this differently. You could first take the reflexive part, the reflexive closure, and then take the transitive closure of that. That would also work. Okay, either way is just fine. But this is a very useful kind of thing. That's why, again, it has its own symbol. So we have here R star, right? That means reflexive transitive closure. And you'll be seeing that a lot in the future.